So we're doing an example, and I think we're recording now, that example. And what we're doing is we're estimating the frequency response function of a system from impulse response little h of t data. Okay, so putting quotes on the data because we're actually going to generate this data ourselves, sort of simulating this measurement process that we're doing for the impulse response. So the idea is that we have a situation where we have, going back to lecture 12.1, we have h of t measured, okay? So we have some system that we have put an impulse into, a direct delta function impulse, and we've measured what the response is in time, okay? And we'll take that time response and we want to figure out what the frequency response function is of the system, or at least estimate it. Now, this equation here is going to tell us how that works. If we had a functional form for little h, the impulse response of the system, then we could just take the Fourier transform of it and we would get the frequency response function, which is that nice link between the impulse response in the time domain and the frequency response function. Even though the impulse response is the response of the system to just this one input, just the impulse, it actually has within it information for the entire frequency response of the system, which is what makes it sort of special and cool. So that's what we're doing here. We're taking this h of t and we're going to take the Fourier transform of it. We're going to pretend like we measured it. Now, this is a useful idea. It's a useful situation, which is we'll take measured data of a frequency of an impulse response, and then we'll take the Fourier transform of it to get an estimate of what the frequency response of the system is. Now, what we're going to do is a very useful thing, and it's very applicable. But if you wanted to get into the details of taking, of measuring the input and the output of a system, and then trying to identify what the transfer function is of the system, if you wanted to get a really good estimate of that, and you wanted a functional form, an analytic form that has like, you know, the polynomials of s in the numerator, polynomials of s in the denominator, or of j omega for the frequency response function. If you really wanted to do that well and fully, then you would probably want to just get MATLAB System Identification Toolbox, which has some really nice tools for doing that, and it has a lot of algorithms built into it for estimating the frequency response function or the transfer function from time domain data. It doesn't come with the student version of MATLAB. It's like a $10 add-on, so I didn't require that you guys get that because we're only going to use it for this. But it's very useful for doing this type of thing. We're just doing kind of a fun example that'll deepen our understanding. This isn't the focus of what we're doing, system identification, but if you're trying to measure the transfer function of a system, the system identification toolbox is really nice for that. Okay. And this is in keeping with my general philosophy on MATLAB, which is that the core language is no better than any of the other ones out there that can do scientific computing, but some of the toolboxes are really nice and better than what's out in the open source world. So this is one of those toolboxes that's better than what's out there that I've seen. So, great. System identification toolbox. If we wanted to get that functional form of H, that would be a good way to go. There are obviously techniques that don't involve MATLAB. MATLAB just has those techniques built into it, but they're very involved, and I don't think that that's important enough to be part of our course. but it is interesting stuff. So the first thing that we want to do is we have to generate this impulse response data, right? This HFT data. So let's see. Generate impulse response data, okay? So we need a system to simulate to get this spoofed or to get this supposedly measured data. Let's define a transfer function as follows. This will be in LaTeX. I'll do the MATLAB equation in a moment. H of S is equal to, let's say, S plus 20. We'll put in a 0 at negative 20. And then we'll say S squared plus 4S plus 20. Okay, so we know how to put a transfer function into MATLAB then, right? So we can say, we'll call our system sys equals TF of, now we have to do the numerator polynomial coefficients, 1, 20 for the numerator, the denominator coefficients, 1, 4, 20, and that gives us a nice transfer function object. So let's just check for fun. Where did we put our poles? Because I didn't actually show where they were. -2 plus 4i. So that's our location of our poles. We've got, it's stable, okay, negative real part. There are non-zero imaginary parts, so we will see some oscillation in our response. And yeah, that's about it from that. So we now let's find the impulse response. Impulse response is pretty easy to compute. We'll start off with a time array. So we're going to give the impulse simulation a time array. That means that we have, what we're going to get at the end is this time spaced out data. And it's going to be related to our the frequency of the sampling frequency. So let's actually do that. Let's define our sampling frequency to be like, I don't know, maybe 30 hertz. Okay. And that means that our time array is going to be 0 in steps of 1 over the sampling frequency, okay, to, let's do also a parameter for the number of time steps. So let's say big N. Big N is equal to, say, 200. So we have to take into account that N being the last one, we have to subtract 1 from it, and multiply it by, or divide it by fs, which should give us our time array, right? Yeah. Okay. So that should be reasonable. Let's take a look at our TA just for fun. Seems pretty good. Goes up to like 6.6 seconds, 200 points. Great, not too bad. All right, so this is our time array, and let's do an impulse response. So so we called the impulse response H before, right? So HA is impulse. We use the impulse function. Just want to make sure. Can somebody confirm to me you guys are seeing this all and my screen is sharing and all that?
Can confirm.
Can confirm. Okay, great. Thanks. I just like had this moment where I was like, oh no.
We're good.
Thanks, Megan.
Yep. We're
Like,
listening intently.
maybe I'm just like talking to myself. And great. Okay, so impulse of cis, and we'll give it the time array as well. That'll allow us to compute that impulse response. Now, we're going to plot that in just a minute. It's going to be interesting to see the plot, but I want to see, I want to add some noise to this, okay? So to make this seem a little more realistic for the, as a measurement, we should add some noise. So let's say noise is equal to, there's this rand n function that takes a vector size essentially, so n by 1, and it gives us a normal distribution of random numbers about 0. So and with standard deviation 1. Now our impulse response to this thing is going to be around like 1, 2, on the order of like 1 to 2. So we don't want a standard deviation in our noise to be on that same order. We want it to be much, much smaller. Let's do like 0.01 as our standard deviation. That should be reasonable. And then we'll take H and we'll call it H noisy now. HA plus the noise. And that's what we'll plot. And that's what we'll do our Fourier transform on, our FFT on. Plot the impulse response. So let's open up a figure. Let's plot the time array and the H noisy. And I already know I'm going to want to have a line width that's greater than the default. So I'll say line width 0.5. And the X label is going to be time in seconds. The Y label is going to be the impulse response. Okay, let's see what we get. All right, not too bad. This is, we can't see the noise too much for that early part, but we see that the noise is not insignificant. This is a pretty nice low noise measurement, but it's reasonable. we just put in a little noise to make it seem a little bit more like measured data, right? So great, that's our impulse response. We've got a little noise in there, it seems realistic. So now we have this data set and we're ready to do the discrete Fourier transform. So the discrete Fourier transform should, or will, I'll say, we'll be confident, will give us an estimate of the frequency spectrum of the system. That is a numerical version of h of j omega. Great. So the first thing we do is we just take the time domain and we just do the FFT on it. So the command, let's see, h is equal to FFT of, and then we're going to, there's a scaling factor we can give to FFT also. Scaling factors are so hard to get right here. And this, I'm a little rusty on my MATLAB. I've been using Python too much. So hopefully we're gonna get the scaling right. I think I can give FFT, I can just give it H noisy, and that'll give me the spectrum in a way that, remember how in Python we did the FFT, it came like the first half of it approximately was for negative frequencies. This is similar for MATLAB. And so we have to do like an unpacking of this. So that we're gonna wanna plot the magnitude and phase of it, but we also have this two-sided versus one-sided spectrum to consider. What we can do is, let's actually look at the frequency spectrum. There's just the two-sided spectrum, and then I won't worry about, maybe later on after this, I'll put in the notes also the one-sided spectrum version. But yeah, so what I'll say is, yeah, let's see. I kind of have to reverse it anyway, so maybe we will do the one-sided spectrum. Okay, so what we'll do, first I'm not going to worry about the frequency scale right now. What we're going to do is we're going to try to unpack this to be just the one-sided magnitude spectrum. So H mag equals, we have to take the absolute value of H. So that gives us, remember how the frequency response function is a function that gives a complex value. So it's a function of omega, which is a real number, but then it returns a complex number. So you could either think of it as real and imaginary parts, or as magnitude and phase. We typically like to think of it as being in magnitude and phase, especially when we plot it. So we'll look at the magnitude, the absolute value of H. There's a scaling that we can do at this point too, and that is, I think we have to divide this by n. And this is an artifact of how MATLAB packs the FFT up. See, I was looking at the documentation of it, and I do believe, yeah, Yeah, so that is correct. You have to divide it by n. And then we'll do, to get the one-sided spectrum, we still have these two halves of it that we have to break up and essentially double one of them. So we can say is H mag equals, and what this does is first step, it takes the absolute value and uses the scale of the number of points. And then it just selects out the first half and the middle, the zero, the DC value. And then it scales everything except the zero, the first value and the last value by 2. So that's kind of the way that we are going to extract this magnitude out. So we'll say H mag. We're just going to keep replacing H magnitude. So 1 to n, or 1 to L over 2 plus 1, which is the first half and then the next value. And then we have to take 2 times, we have to take the first 2 to n minus 1. So go. I think that was the right way to do the scaling. Sometimes I have to go back and check it again, but that looks right. They also show how to do the frequency.
Hey, Dr. Rico.
Yeah.
Is the L supposed to be N? Because we never defined L.
Yes. Did I use L? Oh, yes, N.
Thanks.
Yes. Sorry, they were using L. Yes. And then we can also say that the frequency is, in this case, it's going to be our sample frequency. N is the number of points, and that should give us our frequency scale. So I believe that this, and I'll split these. So compute the one-sided magnitude spectrum, and now the corresponding frequencies, and now we're ready to plot. So let's do a figure. Let's plot f on the x-axis and the magnitude on the y-axis. Again, I'm going to want to see this with a little bit more thickness so that we can read it. And this is going to be okay. X label is going to be the frequency in hertz, actually. We should probably do it in radians per second. So in order to do it in radians per second, we would take the hertz values and we would multiply them by 2 pi, right? We're doing that because the y is going to be the magnitude of h of j omega. Okay. Undefined function f. Oh, I didn't evaluate this. Undefined function x. Did I not evaluate this either? Wow. Just slacking.
You're doing great, Dr. Rico.
Thanks. Yeah. So I have a magnitude plot of our frequency response function. So we see that there's something interesting here. So the magnitude of the frequency response function has a peak associated with it. It's kind of hard to say where it is. It looks like it's around 5 radians per second to me. It's somewhere between 0 and 10, maybe halfway between. We don't have good resolution through here. If we wanted better resolution through there, we would need to have a higher sampling rate. But what we've got is pretty interesting. And I think that what we would want to investigate now is what is so special about 5 radians per second. Let's go back and look at our the original system had, I did this and I deleted it, so what are the poles? The poles were pole of cis, these 2 complex conjugate poles, and we can estimate the natural frequency to be the absolute value of either one of those. So this corresponds to a damped oscillator with natural frequency as follows. So it's just going to be, I didn't save these, so it's going to be the absolute value of either of those poles. So 4.47. Well, what do you know? At around that frequency, our frequency response function magnitude has a peak at it. And that is what we'll call, especially once you get to the vibrations class, a resonance peak, okay? And so the frequency response function shows that characteristic of this system. And even though we just have this like limited data set that's noisy, we can still see it. You can still see that peak. And so even though we haven't looked at any sinusoidal inputs to this function, we just put in a Dirac delta impulse function, we still know that there's going to be a resonance peak somewhere down at around 4.5 radians per second. So, and we saw that show up in this graph here. So that's good news. We could also do something like this for the phase as well. The phase is also, could be computed using this. It's not as good, the estimate's not as good, especially once we get down to these lower magnitudes, because the noise becomes much more significant then. There's a quantity when we talk about measurement called the signal to noise ratio. And when we're up here, the signal's large and the noise is relatively small compared to it. When we're down here, we added a constant value, so, or a constant standard deviation random number. So we see that the signal is almost completely eaten up by noise out here. And when we get to this area of the signal being overcome by the noise, our estimates aren't good, and it gets very bad, especially with the phase shift. But you can do something similar for the phase as well. So that is a sort of example. When I upload it, I'll also include the phase estimate, and I might include, yeah, I mean, that's probably all we need to do. I'll just include the phase estimate too when I upload. So any questions, concerns about that example problem? Okay, good. I will upload this then in a bit. Presumably there's a way to stop recording.